Assalamu alaikum. Welcome to my channel M.Asif Math Corner. Today inshallah we will study about the normal subgroup in group theory. What is a normal subgroup? A subgroup H of a group G is said to be normal if it coincides with all the conjugate subgroups in G. Thus H is normal in G if and only if G G inverse is equal to H. This statement shows us that if it has its self inverses in G or all the left coset and right cosets, the normal subgroup has also named invariant subgroup because it could not be changed. If we change the elements, then it is very it's need to know about that why it's called variant means if we change its elements, then or we are multiplying from left and right side by cosets or by taking conjugate of other elements, then the results will be the same. And it is also, that's why its also name is self conjugate. Here we can see that about conjugates we have read that if a comma b if a comma b belongs to G, if a comma b belongs to G and here is a G and G inverse also belongs to G, then B will be the conjugate of A if we take the G from G here and G inverse from here. It means that B will be the conjugate of A if G multiplied by A from left side and from right side G inverse, or G inverse here and G can be here. This condition give us the conjugates. So here we can see that these are also self conjugates. So this criteria tells us that it is a normal subgroup. So it is the you can show that by symbolically H is a normal subgroup in G. Every group G has at least two normal subgroups, namely identity and group G itself. Identity group is also called trivial and the group G itself is called improper subgroup. The normal subgroups which are different from these identity and G itself, two subgroups are called proper subgroups, proper normal subgroups. This group is trivial, this G is improper, and all other than these two are called proper subgroups. G is improper, E identity element is trivial, and all other are proper normal subgroups. All the subgroups of abelian group are normal because in abelian commutative law hold and AB is equal to BA means when we multiply by B inverse both sides, then B inverse AP give us the same condition which we need for a subgroup. So, and here is another statement that the non-abelian groups, all of those subgroups are normal. Here he told that all the subgroup of abelian groups are normal, and if any other group which is non-abelian but its all subgroups are normal, that has a special name, the Hamiltonian groups. So remember it. Now next, This is the example of Hamiltonian. The Q is equal to plus minus 1. This is a quaternion group and it is a non-abelian, but every subgroup of Q, the quaternion group, is normal. And the second example is the center of any group is normal. We know that the center of group are those elements which commute with every element of G. For example, if we have G is equal to A, B and C, let we take A. AB is equal to BA and AC is equal to CA. It means that A is going to communicate with every element of G, then A will call the center of G. I hope you understood. We take A from G and G from also G and take its conjugate. Commutate or conjugate means same, because AB is equal to BA means if here we take inverse B and inverse B, these B and B inverse become identity. So A is equal to B, A, B inverse, this type of form. So the center of any group is normal. Since zeta G is equal to where A belongs to G and AG is equal to GA for all G belongs to G, therefore the G into zeta G and G inverse are equal to A belongs to G and AG inverse is equal to A for all G belong to G. We have a theorem for further understanding. If H is a subgroup of G, then the following statements are equivalent. These are equivalent means if this is okay, then this is equal to this is equal to this. These all statements are equal to each other, and these all are the definition of normal subgroups. In A he said that H is a normal subgroup. If H is normal, then we can prove this, but we start from here. The normalizer of H in G is the whole G. If actually the normalizer is that if we take some elements from G and communicate with elements with a subset H, we have a group G 1 minus 1 iota and minus iota. We take H is equal to 1 and minus 1. We take every element from G and commutate with H. Those elements commutate or commute, those elements which commute with whole H, those are called normalizer. So if the whole group of G is normalizer, then the normalizer of H in G is equal to complete G. From here we start and prove that from B to C, GH is equal to HG, where G belongs to G, and GHG inverse belongs to H, where H belongs to H and G belongs to G. These are the statements we have to prove. So we start from here, this statement, and then by this statement prove this statement, and by this statement prove this statement, and from this statement we prove at the end a statement that H is a normal in G. Let's start that the normalizer H in G has whole group G. So A implies B. Assume that we start from A. Assume that H is a normal subgroup of G. Then the normal subgroup by definition is GHG inverse equal to the self conjugate, you may say, and when we multiply G here and here, then G inverse become identity and GH is equal to HG, and this is the definition of normalizer. So it means that if G belongs to G, then G belongs to normalizer, and it means that G contain a normalizer, and we know that all the all the elements of normalizer contain in G. It means that normalizer of H in G is equal to G. Hence by A from this we prove this. Now from this we will prove this. From B to C, and in B we know that it was a normalizer, and by definition of normalizer is GH is equal to HG. This is the definition of normalizer. So hence proved. The C statement was this. So from C to D, suppose that GH is equal to HG and G belongs to G, then for the given any H belongs to H, there exists H prime belongs to H such that GH is equal to H prime G. G is the element of capital G and H is this subset. So the H prime and smaller h are the elements of H. From here, when we multiply by G inverse this side and this side, we get GH G inverse is equal to H prime, and we know that H prime belongs to H. So GH G inverse belongs to H, and this is the definition of what we prove that this is equal to this. This was the statement in D. You can see that this was we prove this one, and now from this we prove A. From D to A, if we have GH G inverse belongs to H, then we will prove this. D implies A. From D to A, we are going to prove from D to A. Suppose that GH G inverse belongs to H, where small h belongs to H and small g belongs to G, then we are taking this statement GH G inverse is equal to H prime, this one, where H prime also belongs to H. Now let's suppose that GH G is equal to GH G inverse, where small h belongs to H and these elements contain in H. For all G belongs to G, also for any H belong to H, we can write H like this, because this GG inverse is identity element and this GG inverse is also identity element. So H is equal to H means we can write this H is equal to GG inverse H and GG inverse. From here, what we will do? From here, by changing the brackets, these are the elements of conjugates. These are the conjugates elements. So we put this is equal to H because smaller h or primer H prime belongs to H. So this statement can be write this GH prime G inverse, and this belongs to this set of conjugates of H or normalizer. So it means that this H is contained in this, or by combining both equations we prove that this GH inverse is equal to H. I hope you understood. If you find any query, you may ask in the comment box. Thank you so much.